The quantum internet is coming, and it could change privacy forever. Not because it replaces the web you use today, and not because it magically protects every phone or laptop. The real idea is more specific. A new layer of networks that can move quantum states, connect quantum machines, and make some kinds of eavesdropping visible. That is why governments, labs, telecom companies, and security teams are paying attention. Today's internet sends ordinary bits, zeros and ones. Routers copy packets, amplify signals, and pass data along. That copying is exactly why the internet works at global scale. A quantum network is different. It uses quantum systems, usually photons. Those photons can carry states that behave nothing like ordinary bits. They can be entangled. Their unknown state cannot be perfectly copied, and if someone measures them in the wrong place, the measurement disturbs the system. That is the privacy breakthrough. In quantum key distribution, two users can exchange quantum signals and then check whether the channel looks clean. If an attacker interacted with the signal, the users see extra errors and discard the compromised key material. It does not mean security becomes perfect. Real devices can have flaws. Authentication still matters. Endpoints can still be hacked. But the channel gains something classical networks do not have: tamper evidence from physics. Here is the simple version. Alice and Bob want a shared secret key. They send quantum signals, compare a small sample over a normal authenticated channel, and measure the error rate. If the error rate is normal, they turn the remaining data into a key. If it is too high, they stop. The message itself can still be encrypted with classical software. The quantum part helps protect the key exchange. That distinction matters. The quantum internet is not teleporting your whole video call through a magic tunnel. It is a way to make silent spying much harder on certain high-value links. But the bigger vision goes beyond keys. The Department of Energy describes quantum networks as infrastructure for quantum computers, sensors, and communication devices. NIST highlights three major uses: secure communication, distributed quantum sensors, and connecting quantum computers into clusters. To make that work, researchers need quantum repeaters, quantum memories, precise timing, better detectors, and new network control software. A normal optical amplifier can boost a weak signal by copying it. A quantum signal cannot be copied that way. That is one of the hardest engineering problems. So no, a global consumer quantum internet is not arriving next Tuesday. But pieces already exist. Chicago has operated a metropolitan quantum network over roughly 124 miles of fiber. NIST is working on quantum optical networking testbeds. Europe is building EuroQCI, a quantum communication infrastructure across member states, including fiber links and a satellite component. The first customers will not be ordinary households. They will be governments, national labs, data centers, banks, energy grids, research facilities, and defense networks. This matters because privacy now faces two quantum problems. The first is future quantum computers. NIST has already finalized post-quantum encryption standards because powerful quantum computers could eventually break much of today's public key cryptography. That is, the harvest now, decrypt later threat. Steal encrypted data today, store it, and wait for better machines. The second problem is protecting the most sensitive links after that transition begins. Post-quantum cryptography changes the math in software. Quantum communication adds a physical warning layer for some links. These are not competitors. They are complementary. For most people, the immediate priority is post-quantum migration. Browsers, banks, hospitals, messaging apps, cloud systems, and embedded devices need to move before old encryption becomes dangerous. For the highest security connections, quantum key distribution may become another layer in the stack. But we should be honest. A quantum link cannot fix a compromised laptop. It cannot save a badly managed key server. It cannot prove that every device in the chain is perfect. The best way to understand the quantum internet is this. Classical networks hide secrets behind hard math. Post-quantum cryptography tries to keep that math hard for quantum attackers. Quantum communication adds something different, a channel where observation can leave evidence. If the next decade goes well, you may never see a quantum router at home, but your bank, hospital, cloud provider, or government may use quantum-secured links behind the scenes. The quantum internet is coming in pieces: testbeds, secure regional links, satellite connections, and later networks that connect quantum computers and sensors. The real story is not that hackers disappear. The real story is that silent interception becomes harder, key exchange gets a new warning system, and the race to upgrade privacy becomes urgent. Subscribe to Science in 5 Minutes if you want to stay ahead of the technologies shaping the next decade.